So good afternoon, everyone. My name is Rogelio Sullivan. I'm the project manager at PowerAmerica, and I'd like to welcome you to our monthly technical webinar series. Each month on the first Wednesday of the month at 12, we offer technical webinars on technologies of interest to the wide bandgap semiconductor community. Today's webinar will be given by Dr. Kevin Bai from Kettering University of Michigan. And I'll give you a brief bio of Kevin, and then he'll begin. At the end of the webinar, depending on how many folks we have online, I will ask you to ask your questions by using the chat function, which you'll see along the top menu bar in WebEx. And so if you type in your questions there, I'll read the questions to everyone, and then everyone will hear the answers as well. And I also need to let you know that this webinar is being recorded. And so that's just a requirement. Okay, again, welcome to PowerAmerica. Kevin Bai is our featured speaker today. Kevin received his BS and PhD degrees from the Department of Electrical Engineering at Tsinghua University in Beijing, China, in 2002 and 2007, respectively. He's an affiliated associate professor at Kettering University, formerly General Motors Institute, an associate professor in CECS at Dearborn since January 2017. His research interests include power electronics with motor drive systems, EV battery chargers, auxiliary power modules, battery management systems, and wide bandgap devices. He's the author of a book entitled Transients of Modern Power Electronics, as well as 38 peer-reviewed IEEE journal papers and 34 conference papers. Meanwhile, he holds 7 industrial patents and acts as the associate editor of the Society of Automotive Engineers International Journal on Alternative Powertrains. So with that introduction, I'll turn the webinar over to Dr. Kevin Bai.
Many thanks for the introduction of Rogelio. Again, this is Kevin. For today's presentation, I'm going to talk about the comparison of silicon carbide and gallium nitride-based EV battery chargers. This project was started back to nearly 1 year ago, and the project involved the 3 parties: Kettering University, Pella Electronic Center, and University of Michigan Dearborn. So for today's presentation, we can quickly go through some basic project background, then detail the technical solutions. At the end of the presentations, we will discuss some research findings through the experimental way, then at the end, draw the conclusions. So our team is located in the heart zone of U.S. automotive industries. From time to time, we were approached by the automotive OEMs and suppliers requesting the battery charger development, especially to focus on the single-phase input battery chargers. Even though in Asian market and the European market, there are 3-phase chargers demanded as well. Majority of the requirements are on the onboard chargers. And we do sometimes develop the off-board charger. Right now, there is an argue that maybe 20 kilowatt is a boundary between the onboard and off-board, which we think makes sense because when power goes too high, it will be difficult to fit such charger on board, and the cost of such charger will be higher. For the onboard chargers, we require pretty strict isolation due to the safety issue between the grid and the battery. Majority of the chargers will be unidirectional and the conductive charger, although in the last decade we have witnessed the surge of bidirectional charger and wireless charger as well. Now, if we look at most of the charger we developed, especially for the single-phase input charger, it has to deal with 110 volts in and 220 volts in. So we name all the chargers with 110 volts in. Doesn't matter the input is 15 volts or 15 ampere or 30 ampere as level 1 charger. If the input voltage goes double 208 volts or to 260 volts, the power at the same current input could be doubled as well. So we call such charger as a level 2 charger. And of course, there is, in recent days, DC charger required by more and more electric vehicles. But for such charger, there is really no charger on board. So we only provide 500 volts directly to the battery. So such charger development will be regarded as off-board charger. Doesn't matter which charger we are talking about, we have to comply strictly the SAE standards and deal with communication between the battery chargers, BMS, and the vehicle control unit. Since all the chargers will be plugged into the grid, we need to be careful about the power and high power density. So particularly for the onboard charger development, efficiency and power density are actually quite coupled with each other. Given the fact we have limited space on board for the electric charger, a low efficiency charger will require bulkier and bigger heat sink, which will lower the power density as well. So to increase the power density, increasing the efficiency is a precondition. Now, if we can look back the types of the vehicles we are dealing with, the charger we developed will be the level 2 charger, particularly dealing with plug-in hybrid electric vehicles with smaller battery on board and pure battery electric vehicles with bigger battery pack on board. If we can develop a 6.6 kilowatt charger with such level 2 charger, we probably can finish charging of the conventional plug-in hybrid electric vehicles within 2 to 3 hours. For the pure BEV, it might take longer, but usually like 8 to 12 hours is acceptable for majority of the customers if they charge their car in the garage overnight. Now, 2 years ago, when we started the gallium nitride charger, we worked with Hella Electronics to say, if possible, we can develop a particular charger for the market. Now, this charger, in addition to the high power factor and the low THD on the grid side, particularly will focus on pretty high efficiency, 97% efficiency versus the 94 to 95% efficiency on the market, which means in terms of the power loss, we have to cut the loss half. Same as other chargers, we have to be compatible with low voltage input to high voltage input, low output voltage to high output voltage due to the state of charge drastic change for the battery. When battery SOC is low, the voltage will be low. When it's high, the voltage can go up to 450 volts. Now, another difference is we want to develop this charger much smaller, which means the power density probably should be as big as possible. Let's say 2 kilowatt per liter versus 1 kilowatt per liter. If the charger can realize bidirectional, that's a plus. If it cannot reach bidirectional, that's not a big deal. So based on such specifications, we talk to each other back and forth about different approaches. First approach we were thinking of for the charger will be the conventional development, which is you receive AC in, single phase AC in, through the AC-DC PFC, power factor correction, to boost it to, let's say, 400 volts. This 400 volts is undertaken by a bulkier and a big DC bus capacitor, then goes through a DC-AC inverter on the primary side of the transformer. Then transformer secondary side will induce it to charge the battery. Now, if we look at this topology, overall we have stage 1, stage 2, and totally 3 stages. And it requires the big capacitor on the DC link. And meanwhile, the efficiency, even though we might reach 99% efficiency for each part, when you multiply them together, since they are in the serial loop, you might eventually find 96 below efficiency. So this topology we think is definitely pretty mature and a pretty great topology but to reach our target of the power density and the efficiency, it might be challenging. We, as a matter of fact, have developed a 7.2 kilowatt battery charger using the gallium nitride devices recently. And this is exactly input, single phase input, 7.2 kilowatt. The battery output voltage is a little bit different because this charger is particularly dealing with golf car or airport electric car. But if we don't consider the secondary side, let's take a look at the overall circuit layout. You have pretty bulky DC bus capacitor in the middle. So that definitely will lower the overall power density to any number below 2. So eventually we estimate for such development, it might not be able to reach our efficiency and power density goals. Even if we extend such topology to 3-phase conventional design, meaning still use the 3 stages, let's say what do we have? We, on this charger, will have still electrolytic capacitor because this charger is particularly off-board charger. If on board, we have to replace those capacitors with even bigger film capacitors to deal with the high temperature operation and prolong the lifespan of the capacitor. So even if we extend it to 3-stage, to higher power 3-phase design, such components still cannot be skipped, and we still will see power density below 2 kilowatt per liter. We have another prototype totally using 3-phase 380 to 480 in, charge the electric bus up to 800 volts, totally using silicon carbide devices. We think the switching frequency is already pretty good enough, 400 kilohertz. But let's look at the overall system layout. From the 3-phase in, you have the common mode choke, you have 3-phase inductor, you have heat sink, you have DC bus capacitors. So even though we don't care about the secondary side and the transformer side, we probably see this passive component already occupied nearly 1/3 of the overall system. And the power density for this charger, 20 kilowatt, will be 3.3 kilowatt per liter. But if we shrink it down to 7.2 kilowatt, this power density number will definitely drop significantly. So we were thinking of maybe conventional 3-stage design will give us difficulty to realize high power density. Let's take a look at another topology proposed by ETH back to 2012. So this is a topology where they saved one stage, directly converting the AC into another high-frequency AC, then use induced high-frequency AC to charge the battery through 4 switches. Now, definitely, we can expect that such topology will give us a higher efficiency because one stage is off. And also, there is no bulky DC bus capacitor anymore. This capacitor C1 and C2 are staying here to filter the high-frequency harmonics. But the challenge is the back-to-back connected switches. So we were thinking of, is there any way we can get rid of these 2 back-to-back switches? Therefore, we inspired by another paper from the ETH, we decided to go for this topology. This topology will totally skip the back-to-back switches, will utilize a silicon-based H-bridge operated at grid frequency. Imagine grid right now is 60 hertz. Then we convert 60 hertz AC into 120 hertz DC with the voltage not stabilized. So this voltage profile will follow exactly the grid voltage. And therefore, we don't need the bulky DC bus capacitor here anymore. The power delivery from the grid to the battery will be taken care of by this H-bridge. The dual active, I should say the DAB stage, dual active bridges, 2 full bridges. Now the disadvantage for this charger is the output will have 120 hertz ripple. Now if for some OEMs, they are fine with this ripple. But for other OEMs, they might want to see pretty flat battery current. Therefore, another active filter could be installed to filter the harmonics. Now, another merit for such topology is if we can totally get rid of, totally eliminate the active filter while paralleling another two modules, overall we can form a pretty neat three-phase development to deal with a three-phase charger. So each phase will have their own phase input. Together, even though each charging module will output 120 Hz ripple, but when you add all this ripple together, due to their 120-degree phase delay, really when it goes to the battery, there is no such low-frequency ripple anymore. So we, based on such topology, build two prototypes. One is a single-phase prototype exhibiting the power density around 4 kW per liter, and another is a three-phase charger prototype exhibiting also 4 kW per liter. Now, compared to one of the competitors on the market exhibiting 2.4 kW per liter, such charger definitely is much smaller and much lighter. Therefore, last year, we came to PowerAmerica to say, based on such gallium nitride charger development, is that possible for us to maybe compare these two technologies, silicon carbide with GaN, and say what is the right approach, or what is the merit and demerit of each technology? So we'd like to compare two chargers with silicon carbide and GaN respectively in terms of the efficiency, power density, thermal, and cost. Cost definitely is one of the factors we would like to include because EV battery charger is pretty cost sensitive. So the methodology we adopt here is we'd like to, if possible, use the same voltage level devices. It probably won't be very fair to compare 1200 volt silicon carbide with 650 volt gallium nitride devices. But the silicon carbide devices, based on our knowledge, usually have higher switching off loss. Therefore, it's probably not possible for us to run the gallium nitride silicon carbide charger exactly at the same frequency of GaN devices. So in order to reach the same efficiency, we might have to sacrifice a little bit of power density for the silicon carbide charger. Because the GaN devices we use from GaN systems, whose packaging is different from majority of the silicon carbide, we have to think of redesigning the charger packaging and the hardware layout. At the end of the project, we need to consider the overall cost for two different technologies. So this is the general methodology we adopt to do such head-to-head comparison. Now, if we look at the charger, the devices we are using, the GaN devices are from GaN systems. There are 650 volts, 60 ampere devices, is about a quarter of the size of conventional TO-247 package for silicon carbide or silicon devices. So we can definitely, even before the research activity, can imagine that parasitics for such a device usually is lower, but maybe thermal dissipation for such a device will not be advantageous compared to the conventional TO-247 package. So after this background, we'd like to talk about technical solutions, say how we should optimize the two chargers respectively. First, we need to select the right components. There are many gallium nitride and silicon carbide devices available on the market. And after selecting such devices, we have to consider the right approach, control approach for the two chargers. As I said, thermal design will be critical as well because two types of switches have totally different thermal pad. Magnetics design is not our advantage. We are not very skilled at developing the magnetics. So we asked the help from different magnetics companies, benchmark their products, then select the best one to fit in our chargers. At the end, we package all the components, including semiconductor devices, heat sink, and magnetics, try to reach as high power density as possible. So we, in the beginning of the project, were thinking of using 1200 volts power module of silicon carbide devices. But then we gave up such idea, simply because if we look at the one of the power modules, the scaled size of the power module compared to the 1/2 range of gallium nitride devices is very disadvantageous. So the size is nearly 3 or 4 times bigger. If we use such power module, we will have no chance to reach the same power density for silicon carbide devices. Plus, if we look at the newest power module provided by Wolfspeed, this module is 1200 volts, 400 ampere devices. We think such module is a perfect candidate for motor drive system design. As a matter of fact, right now, our group is using such module to develop a 100 kilowatt motor drive inverter using such module. But for a 7.2 kilowatt battery charger, such module might be overkill. Therefore, we turned the help to the single switches. Originally, we were thinking of let's parallel 3 1200 volt switches to see what's going to happen. But luckily, we find some other candidates which are even better. We have 650 volts, 90 ampere silicon carbide MOSFETs from ROM. So if we parallel 2, we can nearly have the similar performance in terms of the conduction loss compared to 4 gallium nitride devices. And of course, we can use ST 100 ampere devices. And by the middle of the project, we were even provided 160 ampere silicon carbide MOSFETs from Wolfspeed. So if we use such devices, we probably do not need a parallel. One switch probably is enough. So that will definitely help us to save the space of the charger. When we select the switches, we need to consider the different loss. Particularly for semiconductors, we have switching on loss, switching off loss, conduction loss, and deadband loss. Doesn't matter which devices we use, zero voltage switching on is a must. If we take a look at these two figures about the silicon carbide double pulse test data and the gallium nitride double pulse test data, their switching off loss are all pretty lower than the switching on loss. Same thing happens with the silicon carbide devices. In other words, if we want to have high efficiency for the charger, we'd better get rid of the turn-on loss by using the zero voltage switching. Now, for the dual active bridges, the problem for such topology to run at the light load is the potential to lose the zero voltage switching on. Therefore, we have to think of some control algorithm which will allow us to secure ZVS for all power and all voltage range. Now, imagine if my output voltage is lower than the input voltage. For example, we are charging 400 volts battery. Now, we can give a phase shift between the primary side of the transformer and the secondary side of the transformer, which we name it as a GT. Meanwhile, we can also give another phase shift to the secondary side voltage, like this green line, which we name it as WT. So this GT and WT are the function of the time, simply because our input voltage is not stable. Our input voltage is following the grid voltage profile. So these two phase shifts are always changing with the time. Same thing happened with the switching frequency. Only when our switching frequency, two phase shifts are complying with such rules, we can guarantee the ZVS for all switches. So we'd like to check each point to make sure they comply with ZVS. So this is what's happening when output voltage is higher than input voltage. Because another extra phase shift is introduced to the secondary side, we call it as a SDPS control, secondary dual phase shift control. Now, we also need to consider if the grid voltage is higher than the battery voltage. Let's say if the battery is 200 volts, we still have to charge it. What shall we do? Now, as this scenario, we move the extra phase shift to the primary side. So let's say this blue line represents the primary side transformer voltage, and now the green line is actually 50% duty cycle square waveform right now. But the blue line, the primary side voltage of the transformer, is turned into 3 level. So since right now we introduce an extra phase shift to the primary, we name such topology, such control strategy as primary dual phase shift control. So imagine right now we are charging a 200 volt battery. The input voltage is 208. So the peak value will be around 300. So the input of the DAB really is changing from 0 all the way up to 300. In the middle, you have the crossing point between the grid voltage and the output voltage. So when the voltage is lower than the battery voltage, we are going to have the secondary side phase shift control. When these two voltages have the crossing point, they are exactly equal to each other. The topology, the control strategy is evolved to the single phase shift control. While when the input voltage is higher than the output voltage, we will change it to the primary side phase shift control. It looks like such a control strategy is quite complex because you have different modes in the control to implement. But later in the experiment, we can verify it that it's quite naturally switch from one mode to the other. Only by doing this, we could secure the soft switching on for all switches. Pay attention, for DAB side, we have 8 switches. So our goal is to secure ZVS for all switches of all range. Now, when we look at the switching frequency, it doesn't matter the input voltage, output voltage is 400 volts or 200 volts. The switching frequency is always changing. So for GaN devices, it's changing from 500 volts to 500 kilohertz to 100 kilohertz. This is what's happening within one fundamental period. Now, furthermore, if we want to reduce the switching on loss to realize the ZVS, we have to guarantee that the current installed in the leakage inductor of the transformer is large enough during the deadband to deplete the energy stored in one of the switch junction capacitance. So I probably won't talk too much about where this equation coming from, but the minimum current we have to secure for the devices is a function of deadband selection, capacitor junction capacitance, and the leakage inductance. We have to, when we do the calculation, we need to let each turning point of the current, of the transformer current, have absolute value larger than this minimum required current. Otherwise, switch will lose the zero voltage switching on. Now, what are the values we should select for this minimum current? We have 4 gallium nitride devices in parallel. The output capacitance is 2 nanofarad, actually way larger than what we calculated through the data sheet. Eventually, what we figure out the reason we figure out is even though each switch doesn't have too big or pretty small output capacitance, when you parallel them in small spaces, we also use pretty thick polygons in the different layers. So those polygons actually contribute quite large portion of the COSS, which makes our minimum turn-on current for the gallium nitride charger around 7 ampere. which means we have to check all those 6 turning point current value should be larger than 7 ampere. When we use the 2 parallel silicon carbide MOSFETs, we find actually the current is about 8 to 10 ampere, which means these 2 chargers, GaN charger and the silicon carbide charger, could pretty much use the similar ZVS zero voltage switching condition setting to realize the ZVS. That will facilitate our control strategy selection. Now, the second loss will be the switching off loss and the deadband loss. The reason I added these 2 together is because we find these 2 factors are highly coupled for the gallium nitride devices. For silicon carbide devices, we don't find such phenomena. We use -5 volts to turn off the switch very fast to reduce the switching off loss. However, when the current is reverse conducting, when switch is reverse conducting, we find a nearly 7 volts voltage drop across the GaN devices. So we have to be careful about the selection of the deadband. When we select too much deadband, definitely the loss of the deadband will go up. But when we select too small deadband, the current is not enough, not taking long enough to deplete the energy stored in the COSS. Therefore, we might lose the ZVS. So we have to select a sweet point for the gallium nitride charger. For silicon carbide charger, we don't find such phenomena at all. Now, some people might ask, why do we need 4 GaN devices in parallel? This is the way we use to reduce the conduction loss. Parallel MOS switches definitely will help us reduce the conduction loss, thereby meeting the 97% efficiency requirement. If we look at the electrical point of view, from the electrical point of view, each switch is 650 volts and able to handle 60 ampere. But from the conduction loss point of view, the more we parallel, the merrier. Now, when we compare silicon carbide devices and GaN devices head to head, if we use the silicon carbide devices 2 parallel, operated at the same switching frequency as the GaN charger, we will have much higher loss. So eventually, the approach we adopt here is to make their loss nearly similar, but reduce the switching frequency for the silicon carbide charger. So the silicon carbide will be operated at a lower frequency, and the gallium nitride charger can be operated at a relatively higher frequency. If we can look at this figure in more details, we find these 2 silicon carbide devices in parallel could pretty much reach the similar efficiency as 4 GaN devices in parallel. Now, the detailed loss breakdown shows the front-end rectifier for both chargers are pretty minor. Switching loss for GaN charger is much smaller, and both conduction loss are dominant. But the deadband loss for the gallium nitride charger is way higher than the silicon carbide battery chargers. So by reducing the switching frequency of the silicon carbide charger, we pretty much can make the loss nearly similar to for these 2 chargers. This is the loss breakdown at 100 degrees C. Then eventually we lay out these 2 chargers and place them side by side to do the head-to-head comparison. You see the packaging is totally different. The GaN charger are facing, the GaN devices paralleled are facing up and attached to the heatsink. The silicon carbide chargers, in order to save the space, we actually let the switches stand up attached to the wall of the charger. And the transformer in the middle is ported, and the size is larger than the gallium nitride charger. But other than that, there is no majority change. So if we look at what's happening inside the charger, we have AC input in, go through a EMI choke, then go through the rectifier, go to the transformer, primary side and secondary side. The output terminals are located at the same side of the AC input. That will facilitate the charger equipment. So when we consider put these two chargers side by side, silicon carbide charger is a little bit higher, is a little bit bigger. So GaN charger exhibits 4 kilowatt per liter. Silicon carbide is about 3.3 kilowatt per liter. Now, at the last, we would like to consider the thermal analysis to detail the thermal performance. For thermal performance, we use experimental way. We directly measure the junction the case temperature and the heat sink temperature, then see what is the thermal resistance. So based on our test, we find the 4 switches parallel will exhibit 0.6 degree per watt. So given the overall loss, we might reach projected temperature at 90 degrees C, when ambient is about 70 degrees C. For silicon carbide charger, we assign 2% loss, efficiency loss for all the switches and 1% for the transformer. So maximum temperature for the junction is similar as GaN devices, but what we want to point out here is because right now we are using 2 silicon carbide parallel instead of 4 GaN devices parallel. If we just consider switches one by one, one silicon carbide thermal performance definitely is better than one GaN device, given the fact that its thermal pad is nearly 4 times larger than the GaN devices. And if we look at into the more details about the resistance, we find silicon carbide devices we adopt here probably will only increase their RDS on 50% when the temperature is increasing from 25 degrees C to 100 degrees C. But for the gallium nitride devices we are using from 25 degrees C to 100 degrees C, it nearly doubled, maybe even more than doubled. So at the end, we'd like to talk about the cost analysis. So far, we haven't collected enough information from the different vendors about the overall cost. We have 3 approaches we can adopt. One is a GaN charger using 4 pieces of GaN devices in parallel, and the second is 2 pieces of 650 volts, 90 ampere silicon carbide in parallel. And definitely, if possible, we can also try the 1 piece of 160 ampere silicon carbide. If that's true, then we probably can skip any paralleling approach. So as a brief summary, 4 GaN devices versus 2 silicon carbide, we find their conduction loss could be similar. Deadband loss, definitely GaN is higher than silicon carbide. Switching on loss, because of ZVS, they are all 0. Switching off loss, silicon carbide is higher than GaN. Gate drive loss, silicon carbide is higher. Thermal capability, silicon carbide is better than GaN. But given the fact we use 2 silicon carbide parallel while using 4 GaN devices parallel, so overall, I would say from the charger point of view, these 2 devices are equally good. Cost is something we still missing. So if you go to DigiKey to search the cost of the charger of the devices, definitely those numbers probably won't effectively reveal the roadmap of each company. This number is something we'd like to provide by the end of the project. At the last, magnetics design. As we said, we don't wind all those transformers, but we have pretty great company partners to help us provide different technologies of the transformer. And we have ANSYS Maxwell to, along with Simplorer, to do the code simulation. One interesting thing we figure out while we benchmark all these transformers are, it looks like nearly all the transformer company provide the candidates with pretty low core loss, but the copper loss usually is much higher. So we'd like to ask them to give us as thick copper, or I should say as thick lead wire for the winding as possible to reduce the skin effect. Now, experimental validation. This is what we tested at 400 volts when input voltage is lower than output voltage, meaning the input is maximum is 300 volts. So at that time, you have primary side phase shift and a secondary side phase shift, and the extra phase shift is added to the secondary side, and we realize ZVS for all the switches. So this waveform is quite similar to what we simulated. And if you look at the output current, definitely it has the low frequency ripple. Now, we are also able to charge 200 volts. So when it goes to 200 volts, you can see when input voltage is pretty high, higher than the battery voltage, now the phase shift is actually on the primary side. Now, when input voltage, this zoomed area, is similar to the output voltage, the extra phase shift disappears, so the control is evolved into the single phase shift. Now, when input voltage is close to 0, which is lower than output, now primary side, this yellow line doesn't have the phase shift anymore. So you can see the phase shift is control is smoothly evolved into, or from PDPS to single phase shift control, then to the secondary DPS. So this is also the way we secure the ZVS. Efficiency is a very important number for us to compare. If we look at these two chargers side by side, the GaN charger exhibits pretty high efficiency. Silicon carbide charger, we haven't finished the test yet. Hopefully by the end of this month and early next month, we can go all the way up to 7.2 kilowatt. So far, we stayed with around 5 kilowatt. But efficiency number at, let's say, at a 5 kilowatt, if we compare such number, GaN charger is about 96 to 97. Silicon carbide charger is also about, I think, it's about 96 to 97. Their efficiency number is similar. This approach, the approach we adopt here actually give us some pretty interesting phenomena. That the efficiency number you see is not like most of the charger reaching the peak in the middle while drop at the two side. This charger actually the efficiency will always go up with the power going up. Simply because when we run at a low frequency, we have to low power. So the power loss will be big. While when we run this two charger at heavy load, the switching frequency drops, so switching loss actually reduced. Now, with that, I'm going to briefly give a conclusion, the outcome we have for these two chargers. We think this project is a great opportunity for us to compare two types of technologies head to head. What we find out is gallium nitride charger using GaN systems device exhibits higher efficiency and power density, but the silicon carbide charger has the advantage of thermal and maybe cost. We will see at the end of the project. What I want to point out is also that this comparison has its subjective side and objective side. We tried our best to utilize the best devices available and also the best transformer, magnetics, and the thermal packaging. But the reason I said is it has a subjective side is because right now we are comparing the conventional Q247 silicon carbide devices simply because this is a device we can find. It is possible that with technology evolving, we can find a smaller package of silicon carbide devices, surface mounted, or even a much smaller size of the silicon carbide devices. So the switching frequency and the switching frequency can go even higher, and the switching energy could be much lower. That might change the conclusion of such comparison. For this project, we were pretty proud of ourselves that we involved 6 undergraduate students, including 5 company and campus co-op, to provide a pretty strong pipeline of power electronics expertise. We also delivered one short course applying wide bandgap devices to EV battery chargers. You can find it on the VTS website. I think the next step for this project before the end of the budget period will be increasing the power to 7.2 kilowatts from our present 5 kilowatt and collect more efficiency data. If the time is available, we'd like to test the single 160 ampere switches. Even though at the end we might find such switch will give us lower efficiency or a little bit higher power, a little bit lower power density, but it does, once successful, save the effort of paralleling the switches, thereby might expedite the research and development period. I would like to acknowledge all our team members, Hela, UM Dearborn, and Kettering University. I also would like to give the special thanks to Volkspeed to provide us the switch samples. With that, thank you very much, and I'm ready to take any questions.
Thanks very much, Kevin. That was pretty comprehensive and pretty thorough treatment of the subject. I really appreciate it. That was a very good presentation.
Thank you.
So we have some time for questions, so please type your questions into the chat window. I believe there's an option for that at the top of your screen in WebEx. And I'll read them off, and then Kevin will answer them, and we'll just roll right through them until we run out of time. So the first question, Kevin, is how do you deal with total harmonic distortion, or EMI, if switching frequency varies from 150 kilohertz to 400 kilohertz during low changes, especially if the filter magnetics are fixed?
I think that's a great question. So if we look at the charger development, we have EMC choke here. So that will help to deal with the harmonic, the EMI to enhance the EMC performance of the charger. Because the switching frequency is pretty high, we probably don't need too much inductor on the grid side. So that's going to solve the problem of the grid PhD and harmonics. For the transformer design, the magnetics design, as I said, this we just give the specifications for the transformer companies and say this is our switching frequency range. We have to meet all the requirements of the power loss. So really, when we do the loss analysis, it's going to be like localized, linearly localize all the power loss as a different switching frequency zone, then average all of them together to meet the efficiency requirements.
Okay, thanks. The next question is, why is the max temperature limited to 100 degrees C only?
I think that's particularly based upon our simulation design, because if we look at our onboard charger, let me see this. Okay. Our onboard charger is having the ambient temperature usually at 70 degrees C. So of course it can even go to 80 degrees C in the worst case. But when we do the simulation, we find that the case temperature is about, during the simulation, is about 93.5 degrees C. When we, and here is a case temperature. Now the junction temperature when we look at the data sheet of the gallium nitride devices, between the case and the junction, it only has 0.3 degrees C per watt as the thermal impedance, which means really the case temperature doesn't have too much gap between the case and the junction. So we think to set at 100 degrees C probably will give us a pretty good sense about the design. And of course, we can go all the way up to, let's say, 120 degrees C. But usually for the charger development, if we go that high temperature, the charger will degrade in terms of the power. So we don't expect to still deliver 7.2 kilowatt at that high temperature. We'd like to probably drop to half the temperature. And when the temperature keep going up, we'd like to shut down the charger. So this is our design methodology.
Okay. Next question. When you change the operation mode to guarantee soft switching, the dynamics and power flow equation of the converter will change. How can you make sure the converter operation is stable?
Yes, that's a great question. So if we look at the control strategy, this is what's happening when we adopt PDPS and the SDPS together. So definitely you won't see the continuous of, let's say, the continuous of the secondary side phase shift. But what we can find is the primary side phase shift, that GT we adopt here is still quite smooth. So as long as this parameter is quite smooth, we won't see the abrupt change because theoretically, if you look at all these equations are all related to this, are all the functions of this GT. If this GT is smooth, when we implement in the microcontroller, we will see we will see no abrupt change. Actually, this has been validated by our control, our experiments.
Okay, thanks. The next question is, since there's no bidirectional power flow, why choose dual active bridge over resonant converters?
Yes, here is something I would like to talk about. If you look at this charger, essentially, definitely, it is a bidirectional charger. Even though we don't require such feature on the market, but definitely such design in the future will allow the V2G and the G2V simultaneously. Second thing is we did think of how about we just get rid of the secondary side H bridge by replacing them with 4 diodes. But once we do that, you will find out losing ZVS is very probable because this voltage, this DAB primary side voltage is not a fixed voltage. It's changing from 0 to peak at all times. It's going to be very difficult for us to secure ZVS for these switches, these primary side switches, without introducing the phase shift between primary and secondary. So if the secondary side are all the uncontrolled rectifier diodes, when voltage goes high, we can pretty much just lose the ZVS for the primary side. So as a summary, we introduced another extra phase shift between primary and secondary to secure the soft switching. If we have other better topologies which can secure soft switching without introducing these active switches on the secondary side, definitely I think that's going to be an even more attractive approach.
Okay, the next question is, can the dual active bridge switch achieve 0 voltage turn on even when the primary side voltage is 0 or very, very low? Or do they have a minimum primary side voltage that the switch can work in ZVS?
Yes, if we look at this slide, this slide actually happens when primary side voltage is 0. So when grid is crossing 0 point, we have no input voltage. Secondary side is undertaking 400 volts. So if you think about your primary side is regarded as a short circuit. Secondary side is like a 3-level voltage. So when we impose such voltage on the transformer 2 side, we are going to generate a pretty big circulating current. This is why we, at 0 crossing point, impose a ceiling switching frequency, thereby dropping or shrinking such circulating current for the charger. So to answer your question, definitely when input voltage is 0 or close to 0, we will go pretty high switching frequency to reduce the circulating current. But also, meanwhile, keep this number, keep this turning point of the current around the minimum current requirement to secure ZVS.
Thanks. Next question is, your input configuration showed 3 phases, but the most common residential transformer configuration is 2-phase, 208 volts. Does it impact the buffer capacitor size and energy density?
Oh, so let's say my input is actually this is a 3-phase, but the charger we are talking about in this is actually 2 input, I believe, two lines, which is a single-phase input, 208. So all the slides I showed it here for 3-phase is only the extension of such single-phase charger. But all the presentations we did today is based upon the single-phase in. So do you think I answered this question?
Yeah, I think that clarifies.
Okay.
I think that's a good answer. Okay, the last question is, would you please explain the deadband loss again?
Sure. So different from silicon carbide devices, which, let me see this, which has, probably here, sorry, which has a body diode in. So when the device is in the reverse conducting, you probably will see 1 volt or 2 volts voltage drop. Sometimes the voltage will be 3 volts if the silicon carbide device is the high voltage and low current category. But for the gallium nitride devices, there is really no body diode. So when the switch is reverse conducting, it has nowhere to go but go through the 2-dimension electron gas. Now, when it goes through such device, let's take a look at this equation. The VSD, because the current is going reversely, so the voltage drop is from source to drain. Now, this VSD is containing 2 parts: the VGD, the gate to drain voltage drop, and the gate to source voltage drop. So if you minus them together, you get the VSD. This is some basic mathematical operation. Now, VGD, the gate to drain voltage drop, the gate to source voltage drop. Right now, we use a -5 volts. So you think about negative minus -5, that's going to give you +5 volts for this item. Now, VGD, the gate to drain, actually is exhibiting some voltage drop as well, because there's a current flowing through the 2-dimensional electron gas, which will give you the current multiply RDSR as a voltage drop. So the overall reverse voltage drop, reverse conducting voltage drop, is made of 1 voltage drop between gate and drain and the 1 voltage drop introduced by the negative turn-off voltage. So of course, if we can say, if we use 0 voltage to turn off, then the second item will be 0. So you can save quite amount of a reverse conducting voltage drop. But the price you have to pay is when you use 0 volts to turn off, the turn off loss will be going up significantly. So I would admit that maybe -5 is too conservative for this design. It is also possible for us to use -3, -2, or even 0 volts. But when we run at different with different switching off voltage for the gate and source, we might have to reconsider other impact factors like switching off energy and basically just like switching off energy. And also the gallium nitride devices is pretty, I think the turn voltage threshold is pretty low, around 2 volts. So to give a relatively negative voltage to turn off such device will enhance the reliability of such charger, based on our understanding.
Thanks. Are there any more questions for Dr. Bai? Any comments at all? I have a minor comment. I was just, in your efficiency discussion, you focused on peak efficiency, and you showed the efficiency curves for the two different, the GaN and the silicon carbide system. Because if this is an onboard charge, I think they operate below the peak efficiency for a good bit of their operating time. So it may be interesting to look at those two curves on the same graph and the same units superimposed on each other, so it's easier to compare the shape of the curve.
Yes.
In addition to the peak efficiency of either.
Sure. Yeah, I think it's a great suggestion. As I said, we haven't fully collecting all the data yet. We'd like to present those curves in the final report at the end of the project. And also, we actually have another curve to compare the present wide bandgap charger versus the conventional silicon-based charger. So at the low frequency, low power zone, the charger probably doesn't exhibit much advantage because during this zone, our switching frequency is pretty higher. So the switching loss will actually become to kick in. So the efficiency at the, let's say 1 kilowatt or 2 kilowatt is quite similar to majority of the silicon silicon chargers. But when power goes up, you find the majority of the silicon charger efficiency actually goes to peak, then begin to slide, while this charger is keep going up.
Okay, great. Look forward to seeing that.
Sure.
We actually have one more question, or two more. What component in the power supply produces the most loss? Is it the capacitors in both systems or something else?
Can you repeat your question again?
It says, what component in the power supply produces the most loss? Is it the capacitor in both systems or something else? So
if we regard this, I mean, if we by power supply means the overall charger, definitely the majority of loss happening at the devices instead of the capacitors. But when we look at some thermal distribution, we find primarily the devices, the hottest device is not happening on the switch. It's actually happening on one of the DC blocking capacitors on the charger. Because this current will be high AC current, high frequency AC current going through this DC blocking capacitors, that becoming the hottest and maybe also a pretty lossy component. For other power supply, like say the gate driver power supply, that's something we didn't investigate.
Okay. The last question is, the drawback for the single stage is the output voltage ripple. What is the acceptable ripple for the battery side?
I wouldn't say the output voltage ripple because voltage will be pretty clamped by the battery tank itself. if the battery internal resistance is very small, then this ripple will be small as well. The drawback will be, as I mentioned, the current. So this current all this 120 Hertz ripple current will go through the battery. As we said, some of the OEMs, for example, if you look at Nissan Leaf, their charger using the Brusa charger has similar 120 Hertz ripple. They could accept such ripple. But for some OEMs, let's say GM or Ford, they have pretty high requirements for the output current ripple. So to meet their requirement, this charger will have to be equipped with an extra active filter to flatten the charging current.
Okay, thank you. In addition to these questions, you have several comments complimenting you on your presentation and thoroughness. So thanks again, Dr. Bai. That was an excellent presentation.
Thank you so much.
And thank you all for joining us today. Next month's webinar will be on Wednesday, June 7th at 12 noon. It will be given by Dr. Sari Dar of Auburn University on development of an open gate dielectric process for silicon carbide MOSFET manufacturing. So thank you all very much for joining us, and we'll see you again next month.
Have a good day. Bye-bye.
Thank you. Bye-bye.